Hello, so in this video we will talk about relations and their matrix representation, and then we will see how some properties of the relations can be represented by this matrix form. Okay. So by definition, the relation is defined by a subset of the Cartesian product of two sets. So what is a Cartesian product? So if we have A, this is equal to 1 and 2, and B, this is equal to A. So what is a Cartesian product? Cartesian product is written by A cross B, which is equal to 1A, 2A. Okay. So all the combinations of A ordered paired with all the combinations of B. Okay. So we have two combinations here. So any subset of this can be a relation. So a relation can be a null set. A relation can be just 1A. A relation can be 2A, or a relation can be the full A cross B, which is 1A and 2A. Okay, so it's extremely important to remember this definition. Actually, especially in this kind of mathematics, it's very important to start with the definition. Okay, so if you remember the definition, it is always easy to proceed. Okay, now what we want to do is we want to have a matrix representation. Okay, so now let's say we have a finite set. We can say A1, A2 up to AM, and our B is, let's say, B1, B2 up to Bn. Then our matrix representation is given by, this is MR here, this is AR not there. Okay, so matrix representation MR, this is given by, so the journal element can be written as Mij, so which is equal to 1 if the ordered paired AI and Bj belongs to R and 0 otherwise, or AIBJ does not belong to R. So this is a definition of the matrix representation. So let's see an example. So for this one, how many elements do we have? For A, we have 2 elements. So then we have 2 rows here, 1 row and 2 row. And how many elements do we have for B? We have 1 element. So we have 1 element here. Okay. So for example, we are talking about this as a relation. So we are talking about the matrix representation of just 1A. Okay. So first row, and so this becomes 1 and this becomes 0. If this is the relation we are talking about. Similarly, if we are talking about, let's say, let's take a little bit more involved example, just a little bit. So if we have A is equal to 1 to 3 and B is equal to X and Y, and then we have R, this is equal to, let's say, 1X, 2Y and 3Y. Now this is a subset of A cross B, right? Because this is a ordered pair, one from A and one from B. Excuse me. And this is same. This first element is from A, second element is from B, and same with this one. So our matrix representation will be given by, now this row corresponds to 1, this corresponds to 2, this corresponds to 3, this column corresponds to X, this column corresponds to Y. Okay, so if you want, you can actually put these numbers here, okay, just for illustration purposes. Okay, now 1X is in R, yes it is in R, so 1. 2Y is it in R, so 2Y 1, and 3Y is it in, this is in R, so 3Y 1. So we have rest of them are 0. So this is the matrix representation of this relation. Okay, now it is you will see that if you have a matrix representation, it is very easy to check some properties of the relation. So this is what we will do next. Okay, so what is the reflexive property? So reflexivity property is related to a set R from A to A. So then we are checking the subset of this one, this guy. Okay. Now this says that a relation R is reflexive if A belongs to R for all A belongs to A. Okay. So in matrix form, what we will say is, we will say that if we have MR, we will say all diagonal elements must be 1. So this is the condition for checking the reflexivity if it is reflexive. Okay. Irreflexive. Irreflexive is defined by a subset from A to A if A and A do not belong to R. Okay, for all A belong to A here. Okay. So then in terms of MR, this means all diagonal elements must be, you guessed it, 0. Okay. Now symmetry. Symmetry is defined that if AB belongs to R, then BA also belongs to R. Okay. If this condition is true, then it is symmetric. So in terms of matrices, what we say, if MR is equal to its transpose. So what do we do for transpose? Transpose, we flip the rows and columns. So rows becomes columns and columns becomes rows. Okay. Anti-symmetric. Okay. So anti-symmetric is defined as if A, B belongs to R, then BA should not belong to R if A and B are not equal. Okay. If A and B are equal, then obviously if A and A belong to R, then A and A belong to R. So whenever A and B are different, then A and B and A both cannot be in R. What will be the definition for antisymmetric? So in this case, we can say that uh, we have to show it like this. So if we have this is my diagonal line and this is my 1 here, so this has to be 0 here, and if this is 1 here, this has to be 0 here. Okay, but if it is 0 here, then it can be 0 both ways. Okay, so it can be 0 both ways, but for 1, if there is a 1, then its symmetric element should be 0. Okay, so then we will say if a non-diagonal element is 1, its image should be 0. And image is seen with respect to diagonal. Okay. Now the complement is, what does a complement mean? That if A, B belongs to R, then A, B does not belong to the complement. So our M R bar will be replacing 1 by zeros and zeros by ones in MR. Okay, so this is for all these topics here. Okay, now what about composition? Okay, so composition, if we have a relation S R and a relation S, for example, then the composition is typically defined by this. This is applying R to a relation and then applying S to another relation. In this case, what will we do? We say MSR, this is equal to MR and then MS, and this is usually given as the Boolean product. So Boolean product is just a typical matrix product in which so this is plus becomes OR and times becomes AND. So let's see an example here. So let's say our MR, this is equal to 1 0 0 0, and MS, this is equal to 0 1. Okay, this is not very interesting, so let's do one, this one. Okay, so then MSOR, this is equal to MR Boolean product MS, which is equal to 1 times 0 plus 0 times 1 and 0 times 0 plus 1 times 1. Okay, so this is 0 plus 0, 0, 1 times 0 is 0, 0 and OR with 0 is 0. So this is 0, 0 times 0 is 0 and 1 times 1 is 1 and 0 or 1 is 1. So this is my answer for this. Okay, so this is for composition. Okay, and just a side note, the union, if we have two relations R union R, so what do? We do OR operation in MR. And for intersection, it's not hard to guess. We do the AND operation element wise. Okay, so for union we do the OR operation, for intersection we do the AND operation. Okay, now let's do some examples. Let's say we have some matrices here and we want to check whether they are reflexive, irreflexive, symmetric, anti-symmetric, complement and inverse or not. Okay, now we have one matrix like this. We have 1 0 1 0 1 0 1 0 1. Okay, reflexive, is the diagonal elements all 1? Yes, they are 1. Irreflexive, are the diagonal elements all 0? They are not 0. Is the transpose of this guy equal to itself? Yes, it is. If you read it by row wise, 1 0 1 0 1 0 1 0 1 0 1, and read it column wise, 1 0 1 0 1 0 1 0 1. So it's symmetric. Is it anti-symmetric? No, it is not. Okay. What about the complement? So the complement is you do 0 1 0 1 0 1 0 1 0. So for inverse we did not cover it. So inverse is if we have R is represented by MR, so inverse is represented by MR transpose. Okay, so we just take the transpose of this, which is just itself 1 0 1 0 1 0 and 1 0 1. Okay, so now let's say another example. So let's have another example here. we have 0 0 0, 1 1 1 and 0 0 0. Is it reflexive? It's not, because all of them are not 1. Is it irreflexive? It is not, because all of them are um, not 0 anyways. Is it symmetric? No, it is not symmetric. Is it anti-symmetric? Yes, it is anti-symmetric, because if you take this element, what is the image of this? This is the image, because this is the diagonal line and this is the image. So if this is 1, this is 0, and this is 1 and this is 0. So this is anti-symmetric. And for complement, what do? We just flip the ones and zeros. And for inverse, what do? Take the transpose. Okay. Then we have another one. We have 1 1 1 1 0 1 1 1 1. Is it reflexive? It's not reflexive. Is it irreflexive? It's not irreflexive. So, and it is symmetric. It is symmetric. It is not, and it is it anti-symmetric? It's not. So, and then what is the complement? So complement is 0 0 0 0 1 0 0 0 0. And what is the inverse of this guy? It's just the same thing, because it's symmetric. Okay. So this is it about the properties of relations and using their matrix representation. So note that there is another property, which is the transitive property, which is I have not covered here. Okay. So in my experience, I've seen that matrix representation is a little bit tricky to check transitivity, but just for completion, I'll just state it here. So if A and B belong to R and B and C belong to R, then A and C should belong to R, for R to be transitive. Okay. So this is a good mental exercise to check that how does transitivity translate into the matrix relation. Okay. So this is it about the properties, and hope it was easy to understand. Thanks for watching. Hope you liked the video.